Okay, in chapter 11, this is very different than what we were talking about in chapter 10. We're going to talk about a new idea. We're going to talk about what are called infinite sequences. And then we're going to use that concept for the rest of the chapter, starting with 11.2, to talk about what are called infinite series. An infinite sequence, or you can call it just a sequence, is just a list of numbers that's written in a definite order. So this would be an example of a sequence. You don't have to start with 1, but oftentimes we do. You can write it, this would be a sub 1, a sub 2, a sub 3, a sub 4, and so on. You could also write it like this. The sequence, this is called a sub n, from n equals 1 to infinity. So in general, if you have a list of numbers, an infinite sequence of numbers, you can write it like this, or you can actually write it like this. You don't even have to put the n equal 1 to infinity. If you don't put it there, let's assume it starts at 1. Okay? Otherwise, you have to specify it. So let's see. Let's list the first 5 terms of this sequence right here. We're going to start with 1. So if n equal 1, isn't that negative 1 over 1, which is negative 1? If n equals 2, you get positive 1 over 2, and so on. So this would, and so on. Notice how it alternates, and the first term is negative. So these would be the first 5 terms of this sequence. This one, let's see. Do you know what n factorial means? For example, 3 factorial is just an abbreviation for 3 times 2 times 1. We define 0 factorial to be 1. So the first term would be 1 over 0 factorial, and we define 0 factorial to be 1, so it'd just be 1 over 1. Second term is 1 over 1 factorial. 1 factorial is just 1 also. And then the third term would be 1 over 2 factorial. 1 over 2 times 1, which is 1/2, and so on. So you get this. So the first 5 terms are 1, 1, 1/2, 3 factorial is 6, and 4 factorial is 24. There you go. Why don't you hit the pause button and see if you can find the first 5 terms of this sequence. I get this, right? Notice, starting with 1, you get 1 over 2, and so on. See how the denominator is always 1 more than the numerator? This is kind of tricky. This is called a recursive sequence. If you're given the first term and you know that a sub n plus 1 is 5 minus a sub n squared, you can find the successive ones. For example, if the first term is a sub 1 equals 2, the second term would be 1 because you get 5 minus 2 squared, so 5 minus 4 is 1. The third term would be 5 minus this squared. 5 minus 1 squared would be 4, so on. So sequence can be given different ways. Okay, let's go backwards now. Suppose I give you the terms of the sequence and I ask you to find the general term. That's really important that you learn to do this. See the pattern? The top is getting bigger by 1. So if this is n equal 1, I think the numerator is going to be n, and the bottom looks like it's always 2 more than the top, and that's exactly what it is. A sub n is n over n plus 2 for n equal 1, 2, and so on. Let's do another one. This one you have an alternating feature, so we're going to have a negative 1 to a power. The first term's positive, so how about negative 1? Not negative 1 to the n, because that would be a negative 1. How about negative 1 to the n plus 1? And on the bottom, it looks like you have a squaring going on, right? So this might be n squared. Alright, why don't you try this one? Hit the pause button and see if you can find the general term for this sequence. I get this. Notice the first term is negative, so you could use a negative 1 to the n here. And you have an n squaring and an n plus 1 on the bottom. Nice. This one's kind of tricky. This one is actually it reminds me of a trig function. That's 1, then it's 0, then it's negative 1, then it's 0. Does this remind you kind of cosine? So you have to play around with it, but this might work. Cosine of n pi over 2. You see, when n is 0, you have cosine of 0, which is 1. What about cosine when n equals 1? You have cosine of pi over 2, which is 0. And when n is 2, you have cosine of pi, which is negative 1. So this will do it. Pretty interesting, huh? Anyway, what does it mean for a sequence to converge? Very important. This is the key idea. Well, I guess it's what you would guess. A sequence converges if the nth term is getting close to some number L. The terms get closer and closer to some number L. The bigger n gets, the closer it has to get to L. In that case, we say this sequence converges. Not all of them can converge. Here's the idea. You know, if you have a a sequence, and these dots represent the a sub n's. As n gets bigger, the a sub n's are getting close to some value L. They don't have to be less than it. They could be above it and below it and so on, as long as you're getting closer to it as n gets large. Okay, more formally, using an epsilon definition, I guess the question would be, how close does a sub n have to get to L? And the answer is arbitrarily close. So what does that mean? Well, for any epsilon, think of epsilon as this band around L. For any epsilon, the a sub n's have to get in that band eventually. What does that mean? They have to get in that band. That means there has to be some integer, capital N, so that for all the n's bigger than n, if n is somewhere out here, for example, the a sub n's have to be in that band. All of them do. That's the formal definition, like we did in chapter 2 when we were talking about limits of functions. The limit of a sequence is exactly the same idea. In fact, very shortly we're going to use functions to compute limits of sequences as well. So it's the same concept you were doing in chapter 2. In fact, this is what the theorem says. This theorem says if you have a limit of a function equaling L as x goes to infinity, we know what that means from chapter 2. And suppose the function agrees with the terms of the sequence at the integer values, then the limit of a sub n, since the whole function is getting close to L, don't the a sub n's have to get close to L too? Because the a sub n's are f of x's. If all the f of x's are getting close to L, then the a sub n's do too. Here's the idea. Look, if you have a function whose limit is getting close to, if the limit equals L, then all the f of x's can get arbitrarily close to L. But the a sub n's, the terms of the sequence, are specific points on the graph of f of x. So since the whole graph is getting within any epsilon of L, so are the a sub n's. So that last theorem is really good. That means that if I ask the question whether a sequence converges, all you have to do is consider the function. F of x is x plus 1 over x in this case. Does the limit as x goes to infinity of f of x exist? Yeah, using L'Hopital's rule, you could just, since this has the form indeterminate form infinity over infinity, by L'Hopital's rule the limit's clearly 1. So you can literally think of the function where the a sub n's are points on the graph of f of x. You can think of it in terms of chapter 2. And what does it mean for a sequence, the limit to be infinity? Well, that means that the a sub n's have to get bigger and bigger. So what does that mean, the a sub n's have to get bigger and bigger? Well, they have to get arbitrarily big, just like in chapter 2. How big do the a sub n's have to get? Well, for any integer m, there is an integer n, so that if little n is bigger than big N, then the a sub n's will be above whatever high bound you set. The a sub n's have to get higher than that. That's the formal definition of what it means for the limit as x goes to infinity of f of x to equal infinity. So it's the same exact definition. Since the a sub n's are points on the graph of f of x, we can apply the same definition. So if you wanted to compute this limit right here, again, the trick is you can think of this as the function f of x equals x squared plus 1 over x. In fact, even though we don't write f of x, we're using the same reasoning. You can leave it like this. You can leave it in terms of n's. You don't have to compute to f of x's. This has the form infinity over infinity. So by L'Hopital's rule, you take the derivative of the top, or derivative of the bottom, and sure enough, this limit equals infinity. Okay, let's do a few more here. So the question here would be, determine if the sequences converge or not. So we're asking the question, as n goes to infinity, what happens to this one? Well, what do you think happens to this? If n is 1, it's negative 1. If n is 1, it's negative 1. If n is 2, it's 1. If n is 3, it's negative 1. You see how it oscillates back and forth? So the limit doesn't exist. All the a sub n's are not getting close to any one value. So because the graph oscillates, does not exist. How about this one? This one, You might want to think of this in terms of our Math 151 ideas. Remember, you can look at the function square root of 2x squared plus 1 over x. What is the limit as n goes to n infinity of this? Well, you can use all your limit laws. If this were chapter 2, you could say this is the limit of the square root of the whole thing, but when you bring the n inside the square root, it becomes an n squared. Our limit laws say you can remove the limit inside the square root as long as it's a positive number and the limit exists. Once you're in there, I skipped a step here, but you could use L'Hopital's rule. It's clear this limit inside the square root is getting close to 2, so therefore the whole answer would be square root of 2. How about this one? What does this sequence converge? What is the limit as n goes to infinity of the inverse tangent of n? Perhaps we should look at the graph of inverse tangent of x. Remember, these inverse tangents of n are points on this graph. So if as n goes to infinity, if the entire graph is getting close to pi over 2, so are those points on the graph, which happens to be the a sub n's, inverse tangent of n. So if the whole function is getting close to pi over 2, then the inverse tangent of n is also. How about cosine of n? What do you think? What do you think about whether or not this sequence converges? This is cosine of x. Cosine of n would be random points on this graph here. So they're going to be arbitrary points on the graph, and they're not going to be getting close to any one number. So limit does not exist. How about this one? A sub n is cosine 1 over n. Let's apply our limit laws from chapter 2. We can bring the limit sign inside the cosine. So what does the limit as n goes to infinity of 1 over n equals 0? And what is the cosine of 0? It's 1. There we go. So computing limits of sequences, we can apply all those limit laws from chapter 2. You can think of them as points on the graph of the functions. Okay, we'll do more of this next time. Bye-bye.